I switched off the visualizer because I want to hypnotise people.
Huh?
It wasn't for me. I get very worried if someone else shows the abstract before the talk. It's almost now for you to actually do what it says up there. Excellent.
So we don't go by that clock.
I think that clock maybe.
Okay, good afternoon, everyone. Welcome to the Maths and Stats Colloquium, first one for the semester. Yeah, please come through.
Station Thomas at the door.
So we hope to have some few of them this semester. So if anybody wish to give a mathematics stats colloquium, please let me know. Okay, really appreciate it. If you got any visitors coming through the university, yeah, okay. Okay, so I put a black and white picture so that you can see black and white picture of Michael. All right, he's in color. Our talk today is by Professor Michael Small. You all know him, he doesn't need introduction. And he's going to talk on a qualitative guide to chaos. After this, please join the speaker for refreshments in the milk, okay? Those who don't know, please follow the people, okay? Thank you, Michael.
Thank you. Thank you all.
Thank you all for coming. I had a look. This is actually the fifth colloquium that I've given at UWA, so in the maths department. So I figured this is my supplementary deferred supplementary colloquium. If I pass this one,
Why?
then maybe I get to give a seminar. So I had this picture up when some of you came in, and exactly what it is doesn't matter, but just to set the scene of what I'm talking about. So the object that I'm going to spend all of the time talking about, once I start my timer so I know how long I'm talking for, is a chaotic attractor. And that's what's visualized here. If I start it again, all the little blobs are points. They're different initial conditions in three-dimensional space. So this is in 3 space. You can spin it around. So each of those points think of as a state, and it's moving according to some rules in this three-dimensional space. If I take one of those points, and apologies for the sloppy programming of whoever did this, and it's not me, but it's a fantastic website anyway. If I take one of those blobs and follow it around, the path that that blob traces out is the white line. Okay, that's the attractor. Right, so yes, there is a slight, it's not quite, but use your imagination. So the blobs are moving around, they trace out the path, which is the white line, and that's what we call the attractor. The rules of the system that govern the system is a set of differential equations. This one's called the Thomas system, named after some famous person named Thomas. someone else. And yeah, and it's a differential equation, so there's rules governing it. But all I care about is trying to describe the properties of this system. Okay, so let me put that away for now and go back to the talk. And if I plug this thing in, I can walk around the room. I also discovered that UWA has got these remote control things here, so you can remote control the computer, but they're chained to the computer. So probably someone didn't think that all the way through, but never mind. Okay, so oh yeah, and quick plug for the UWA Data Institute. They're sponsoring me, or at least they gave me a T-shirt to wear, so I've got the T-shirt on. And what you do is remotely related to data, have a look at the UWA Data Institute webpage and come along and join up and all those sorts of things. This talk is going to be about the things that we do with data, but it's not going to actually involve any real data. Okay? All the data and applications, I'm going to save that for another day. So it's just about the approach to understanding problems with data using applied mathematics. Okay, and I call it qualitative, but what I mean by qualitative is I'm interested in descriptive understanding of the chaotic dynamics rather than solving the equations, which will become clear in a minute. So before I talk about that, I should probably start with, well, I don't have to, but I'm going to start with a bigger question. I'll assume, first of all, that the question is worth asking, and the question is not relating to a null set, so there is something called applied mathematics, and we might want to ask, what is it? Well, anyone that's applied for an Anzium PhD scholarship will have a ready answer for that. And Eugene, where are you? Yes, so we have the 2022 recipient of the AF Pillow PhD Scholarship Award in the room, and he got it because he read this document, understood it, and wrote a lovely essay which convinced the judges of how his research relates to applied mathematics. Fenton Pillow was Professor of Maths, Professor of Applied Maths, I think he was appointed as, at UQ in the 60s. And at the time when he arrived there, he gave this opening address, like his welcoming address, which focused on what is applied mathematics. It's an interesting read. I apologise in advance for the use of gendered pronouns, which maybe are not so appropriate in 2022, but he was saying this in 1965, and in all fairness, it was probably an accurate description of the room he was talking to. The thing that, okay, so if you try to interpret, so first of all, A.F. Pillow arrived in Australia from one of those agricultural universities in the UK and followed the traditions of both Cambridge, Oxford, and the other one, Loughborough, was interested in fluid dynamics. Right? Long-standing classic problem, and at the cornerstone of a lot of what people were calling applied mathematics back then. Applied mathematics was kind of struggling to define itself as a field because it was also something that engineers used to do because they had the applied mathematics or the mathematics to do that. And so he came to Queensland and wanted to set himself up as an applied mathematician, and so gave this lecture about why applied mathematics is a useful and necessary field. The only bit that I would like to focus on here, and again, go and read it if you've got some spare time, it's a fun read, is the idea of a model. So I won't go down to the level of jokes about the difference between pure maths and applied maths. We can do that later after the wine and cheese. But the thing that he's thinking about is there's a model of reality, and applied mathematics is a way of understanding that model using the tools of mathematics, developing the tools of mathematics and using them to understand that model of reality. And essentially, if you read this speech, thinking about it in the way that he was thinking about it, it's clear that he's talking about solving differential equations. As they always say to latecomers, Melinda, there's seats down the front.
I've just been told.
So he's talking about the Navier-Stokes equations and generating solutions to that, or approximate solutions to that. And that's fair enough, but that's far too hard for me. The sort of applied maths I do is looking at systems which we have no hope of ever solving, even in an approximate form, and so what we do instead is try to describe the dynamics of that system. Right? And so that's what I mean by qualitative. Whereas I might try to understand the flow of fluid in a pipe by making approximations and solving in a particular regime, understanding that. That's all too complicated for me. I'm just thinking of systems like that one that I showed you earlier, where I want to seek out a description of that system. Right? So that's the way that those blobs are flowing around in space. I also like the phrase that applied mathematics, in essence, represents an attitude, an approach, a way of thinking. Makes it sound far more exciting than actually it is, to be honest, but that's a nice thought. About the same time, so that was 1965. About the same time, someone who wasn't a mathematician, applied or otherwise, was working for the Bureau of, well, working for MIT, looking at meteorological problems, trying to understand problems related to fluid flow. And in particular, he solves a system numerically, and all of the solutions that he finds are unstable, and almost all of them are non-periodic. Why is that interesting? It was kind of, and so apologies to anyone that's done 3A7 or Math 3021 under Thomas, who would have bashed this into you already. But he got these equations for convection rolls in the atmosphere, and he set about integrating them. And when I say he set about integrating them, there's a story behind that as well, which I'll get to. He set about integrating them, solved them, and then his computer broke down. So he took the last point of his trajectory, went a few points back from it, chucked those initial conditions into the computer and started it again, and found that the trajectory he got didn't match the other one. In other words, in simple terms, he integrated these equations, got a trajectory, tried it again with the same initial condition, got a different trajectory. And what was going on was the readout that he was using as his initial condition was not printed to the same number of significant figures. So there was a small error in that initial condition. Essentially, he discovered that numerically integrating these three-dimensional system of ODEs, integrating a three-dimensional system of differential equations, he found that the same, or very close to the same initial conditions, gave different trajectories. Deterministic, non-periodic flow. The idea that the non-periodic part could be anything other than just noise was kind of a big deal. The paper is kind of pretty much a classic. So those are the equations in their original setting when he published this in 1963. And again, I'll explain in a minute, my use of the words he is not strictly correct. He drew this picture, which is supposed to represent the Lorentz system. We've got better at drawing these things, but these bars, these isopleths, are sort of level surfaces of that, so you can imagine trajectories flowing around the surface going up, and then there's a folding with two pieces at the back here where they get merged in here and come back down again. Right, so it's very hard to visualize from this picture. I'll do better in a minute, but I've got more than India ink at my disposal. The other thing that he did was look at trying to describe the system in a more, so he can't solve the equations. No one knows how to solve those equations. By solve those equations, I mean write down a function x of t, y of t, z of t where the right-hand side satisfies them. That's not possible. What we're doing instead is numerically integrating them. But we can try to describe what's going on. So the equations generate things that look like oscillations. They go up and down. If we look at the peak of successive oscillations versus the next peak, right, how high each oscillation is versus how high the next one is. That's what he's plotting here. Right, so it's a very simple relationship between the height of a peak and the next peak. This picture, for mathematicians, was kind of a big deal because it's a one-hump map. It's got one bump in it, goes up to a maximum and comes back down again. And it was understood that this meant you could describe this using ideas established already in mathematics in terms of dynamical systems for generating non-periodic orbits in that map. Right? But the non-periodic orbits in that map now meant there was non-periodic orbits in that flow, in the continuous thing. Okay, so where am I going with this? Well, first of all, I alluded to the fact that I said several times that Lorenz did this, Lorenz did this, Lorenz did this. If you read the paper, there's a brief acknowledgement at the end of the paper. And if you read the acknowledgement, there's a couple of things that strike you about it. First of all the interesting bits, he's acknowledging someone else. Second of all the hard work. Well, there was some Dr. Barry something or other, but all the hard work was done by Miss Elaine something. And Miss Elaine Fetter this is her footnote in Science as the person that did the computer programming, did the integration, and did the visualizations of this paper. But Lorenz wrote it. Not trying to belittle Lorenz's contributions, but just saying there are other people here in the story as well, and it's quite interesting how they're treated differently then versus now. Now, I will just zip back to this other picture here. So this is not my work. This is just a website that I stumbled across. This is the Lorenz equations here. There's probably a picture of them here, which I can zoom in on. It's kind of a fun little toy. There's various different differential equations. So that's the picture that he was drawing, right? The two halves folding over and joining together. In 3D, it's much easier to see what's going on. And again, you've got the idea of points, those blobs, moving around. And now you can see why it's called an attractor, because you start those blobs off and they get drawn down onto it. When they get onto it, they start to spin around. And the path that they trace out eventually will follow something like the lines that you see there. Okay? So this is a chaotic system. We can't solve it. We want to try and understand it. And that's where the qualitative part in the title of the talk comes from. Okay, so that's Lorenz's story. So so I alluded to the idea of chaos and maps, and so that was this picture here as a map. It's a one-dimensional map of the peak to the next peak. 1975. And it's kind of funny going back and looking at these old papers that, on one hand, are kind of the cornerstones of the theory of chaos, but on the other hand, are going through things which nowadays we take for granted in a very simplistic almost way. So Lee and York were considering maps, simple maps from xn, so you have a value x, your map takes it to a new value, xn to xn plus 1, xn plus 2. You can write down that sequence of values. This is a sequence of such values. Right? And they proved a theorem in this paper. And the theorem, and I apologize to my more rigorous colleagues, I will state theorems rather loosely, just to give you the general idea of what's going on, rather than to be 100% precise. But the theorem is, you've got a continuous map, and if you've got a periodic point with period 3, so that means you've got an x, which maps us to a y, which is not x, which maps to a z, which is also not x, which maps back to x. Right, so period 3 means something which recurs after 3 iterations of the map, but not 1 or 2. If you've got a period 3 point, then you've got periodic points of every period. One-dimensional map. And I show that I can go from x to y to z back to x. And that's enough to say I've got something of every period. If that doesn't surprise you, please explain to me why it doesn't surprise you. The second property is the Lee-York definition of chaos. And it says that I can take sets in that domain, so bits that I am mapping around with that map. So I take some blob of, in this case, my interval R, but my space, my interval J, take some chunk of my interval, and that interval becomes scrambled in the sense here. So points within the interval become close together and move apart. Imagine it kind of like mixing up an omelette or something, right? You've got a mixing vat, you put 2 jelly beans in it, you mix it up, the jelly beans spread out, come back together, spread out, come back together, over and over again. That's scrambled. So it's scrambled in the sense of scrambled eggs with 2 jelly beans. So that's the definition of chaos according to Lee and York. Well, yet not exactly. Well, it is exactly, but some time ago, I actually met York on a boat going up the Yangtze River at a bar on the boat going up the Yangtze, and I didn't drink that much because I can still remember what he told me. And basically, he said, well, yeah, well, there's that Lee-York thing, but there's lots of properties of chaotic systems, right, rather than a strict definition. There's lots of ways there is a strict definition, and you can think about things satisfying that definition if it's being chaotic, but you can also think about it purely in characteristics of things that are chaotic. So, for example, some of you would have heard of fractals, so those fancy, rough, lovely little pictures that you have with complicated boundaries. A chaotic system may have a fractal boundary, doesn't have to, but things with fractal boundaries may be chaotic, doesn't have to, but there's a correlation between those two things. Sensitive dependence on initial conditions, that's kind of like a restatement of the scrambling up, except that what it's saying is that those 2 jelly beans spread apart exponentially fast. So that's what I was saying with Lorenz when he was integrating those equations. When I say he integrated those equations, he had initial conditions that were close together and integrated them out, and they diverged rapidly. Deterministic but not periodic, not predictable. That's that deterministic aperiodic flow. Topological mixing, that's exactly the scrambling. Periodic orbits are dense. Well, if you've got periodic orbits of every period in an interval, then they're going to be pretty close together. But more appropriately, it looks irregular, but it's not random. That's what we're mostly interested in here. And the sort of systems that I study are actually a little bit complicated or simplified, depending which way you look at it, further still. There's a couple of pages here of text with notation and stuff. That's for people that like that sort of thing. If you don't, then don't worry too much. Again, it's just setting up the machinery that I'm using to describe the objects that I'm interested in, rather than something I'm going to rely on to prove stuff later on. So I'm interested in dynamical systems. So these are things that essentially, skip down to this. You've got some function. It's a function of time and space, all right? And what that function does is, if I have an input z, phi t of z tells me where z goes after some time t. Okay? So I can take my point z, and I can map it forward and backwards sometimes z. Phi 0 of z, where does z go after time 0? Well, it's z. Right? Where does it go after 2 times t plus s? Well, it's the same thing as going forward by one of them and then going forward by the other one of them as well. Okay? For those of you that have got through 3A7. This is all revision, but typically what we're talking about here in real applications is we've got some vector field, right? So we've got some system of differential equations. You can think about that system of differential equations as a bunch of arrows in space. And those arrows just tell you where to go. So every point in space has got a little arrow. That little arrow tells you where to go next. Right? F of z are those arrows. Your point in space is z. F of z is the arrow telling you where to go from point z. We write that down in mathematics as z dot is equal to f of z, differential equations. And this thing that I called the evolution operator of the dynamical system, well, what I mean is it's a solution to that vector field. Right? Okay, so that's just the notation. The reason I'm putting this notation up here is really for this slide, for those of you that were familiar with the previous slide already. What I'm interested in is not the dynamical system itself, but the output of some measurement of that dynamical system. So I've got a continuous system. Think of those blobs moving about in that 3 space that I showed you at the start. And I'm going to measure some property of that blob at regularly spaced time intervals. Right? And it's just a scalar, so it might just be how high in one direction that point is. I measure it at regular spaced time intervals. So I've got that blob moving about, and I say, what is its position along the horizontal axis at each point in time? That's my xi's here. At time 1, its position may be something. Time 2, maybe something else. And the question that we're interested in is, I don't know what the differential equations are. I've given up all hope of trying to solve them before I even started. I've made measurements of them, though. And these are those measurements. What can those measurements tell me about the dynamics of the system underneath? Right? What can I qualitatively, and qualitatively here involves numbers. Qualitatively, what can I say about that system without solving it? So there's a fairly famous fundamental theorem in this area called Tarkin's theorem. And for a sigh of relief, I realise that I've got the apostrophe in the correct place, so I won't be read for that later on. Essentially, Tarkin's theorem says that actually this situation is pretty good. As long as I measure one property of my blobs moving about in space, I measure one property. No hanger on, Ed. I was expecting to get some good questions from you, from you number 2. You've got one point moving about in space, and I'm just measuring one property of that point over time at each regular points in time. And that's all I need to know the whole system almost always. Right? So the theorem has got this lovely word generic, which I won't explain. Anyone wants to pick it up. Essentially, it means that, well, actually I will explain it. Essentially it means that if it doesn't work, then you just move the system a little bit and it does work. But what I'm doing is I'm taking my observations at regularly spaced intervals and taking a sequence of them to form a vector. My scalar turns into a sequence of vectors. Each of those vectors is made up of successive points. There'll be a picture in a minute. Each of those vectors is made up of successive points of the scalar, and the way those vectors move about, well, that looks exactly the same as the way those blobs move about in that picture that I started with. Right? Measuring one thing regularly spaced in time and reconstructing vectors from it in this way gives me something which looks the same as the original attractor. Almost always. The other interesting thing about this is the original paper here was, okay, we moved forward a bit, we're now up to the 1980s, so what I'm telling you is only, 41 years out of date, but we'll get there. In this paper, they were trying to reconstruct strange attractors, but they were also trying to do it by using the Fourier power spectrum. And a lesson to all those engineers out there. last phrase there. I doubt whether the power spectrum contains the relevant information. Give you a hint, it doesn't. Okay, so now my presentation gets really high tech. This is my picture of what's going on, what I'm describing to you. There's 3 parts, so follow the arrows. Start over here, go up here, then go down here. Here I am in maths land. I've got some manifold. So I've got some space embedded in some object, right? Think of this as Euclidean space. Think of this as Rn, if that makes you happy. In that subspace of Rn that I'm interested in, I've got a vector field. That's a whole bunch of arrows. Those arrows tell me where to go next. Right? They're my signposts telling me which way my solutions flow. Here is my one state, my one blob, which I call Z. And as I move that blob forward and backwards in time, phi tz, that paints out that curve, that red line, which is where that z point goes as I move time forward and backwards. Okay? Right, so this can all be thought of as differential equations, just like you've seen many times or sometimes before. But now what I do is I take, as I observe that phi t of z as it moves along this thing, and I measure it at different times. Right? That gives me, through this measurement function, that gives me a time series, a set of scalar numbers. That's what I'm drawing up here. Those are my measurements in time. I then construct vectors from those scalars by maybe taking, so I take the first 3 to give me my first vector, then I take the next 3 to give me my next vector, the next 3, next 3, next 3, so on and so on. Each of those triples of blobs here is a vector in 3 space, so that's one of my points in here. So the way I move from this vector to this next vector tells me how I move from this point in 3 space to this point in 3 space, and the way that I move around this object is equivalent to the way that I'm moving around this object. Okay? There's a lot of technical words behind things like equivalent and almost always, which obviously I'm keeping from it at the moment. But that's essentially it. That's the entire mind space that I'm working in. So that was 1981. And that works really well. Tarkin's theorem says you can do this generically, meaning it almost always is all going to work almost everywhere all the time. Except when you've got real data. So one of the good things about maths theorems is they tend to involve things like infinitely long time series and infinitely high precision and continuously differentiable measurement functions. Those things tend to not exist in real life. Most time series are actually not infinitely long. Most measurement processes can't measure things infinitely often. And most digital observation functions are not continuously differentiable, right? And Tarkin's theorem involves all of those things being prerequisites. None of them happen in reality. So what we get in reality is the ability to almost do what was intended in the theorem, and it works quite well in practice, even though the lovely theorem that we've proved doesn't actually hold, strictly speaking. So that leaves us in the situation where we might want to seek out other methods of doing the same sort of thing that work better with real data. And so the reason I've spent 30 minutes introducing this, and I just look at that clock and panic, the reason I've spent 30 minutes introducing that is because it kind of motivates where I'm going next with the newer ideas that we're using. So this is a map. This is the function x equals x. Not too complicated. A slightly more complicated function. This is the function x of, well, I plus 1 or n plus 1, whatever. The next one is the current one in this quadratic, the logistic map. Right? So where the current point goes to between 0 and 1 is mapped out here. For a choice of lambda slightly less than 4 for some reason, but whatever. If I apply that map twice, right, so this is x, and the green line is xi plus 2 from xi. Right? Where does the second derivative of that map go? The blue one's the third iterate. Right, so now I'm plotting on the same picture here. The black line is x, the red line is black line is xt, red line is xt plus 1, green line is xt plus 2, blue line is xt plus 3. Did I do one more? Oh no, I didn't. So I've got xt, t plus 1, t plus 2, t plus 3. And looking at those successive values, just like in Tarkin's theorem, gives me a description of my state of the system. Except I'm going to do something more to restrict that state of the system to make it work better in situations that occur in the real world where I've got noise. First thing I do is I look at the order in which those points occur. Right? So if I look at x of t as 0.3, then x of t is less than x of t plus 2, which is less than x of t plus 1, which is less than x of t plus 3. Right, see what I'm doing? Right, the order in which the points occur changes in each of those regions. So here, the green one, x of t plus 2, is less than x of t, is less than x of t plus 1, less than x of t plus 3. So my state, my system, can be characterized by the ordering of those iterates of the map. Right, so for each region, I'm now reducing the state to an ordering of the integers 1 through n. An element of a permutation group, for those of you that like that sort of thing. And I can go down and list all these things. That's them there. A quick warning for anyone that really likes these things and looks at them too closely. I'm using two different conflicting notations for elements of permutation groups. So don't look at the numbers too closely or else come and ask me later. There's a mapping from one to the other that makes them work. But for each ordering of those things, so here what I'm saying is between 0 and 1, between 0 and 0.7, this first region, x of t is less than x of t plus 1, less than x of t plus 3, less than x of t plus 2, t plus 3. So the ordering, well, later on I call this 1, 2, 3, 4, but I'm calling it 4, 3, 2, 1. But they're the same thing, right? Turns out that that occurs with probability about 0.17. Same thing with all those other combinations. Furthermore, some of them occur in two places in the interval map. And so you've got some probability of some particular sequence occurring. The other thing you'll notice, question for the audience, how many permutations of the numbers 1 through 4 are there? How many lines are there? 1, 2, 3, 4, 5, 6, 7, 8, 12. I'm missing some stuff. Well, actually, I'm not missing some stuff. There's stuff that will never occur for this deterministic map. Right? There's certain sequences of orderings of those things that just will not happen between x of t, t plus 1, t plus 2, t plus 3. And this, in and of itself, is quite important because if I look at a time series from a logistic map, it kind of looks like a sequence of random numbers. But this ordering is something that you won't see in this time series, but you will see in random numbers. So the expectation that you get sequences that do not occur and that the sequences that do occur at fixed frequencies is actually a characteristic signature of chaotic dynamics like this. Okay, so what I'm going to do with that now is I'm going to take those sequences. So the other thing I should disclaim is that in in time series analysis and applied dynamical systems, we always start with the logistic map because everything works for the logistic map. You understand it very well. But now I'm going to take the same sort of thing and I'm going to ask, well, if I'm in this particular sequence, 2, 1, 4, 3, what sequence do I go to next? Okay. And so here I am, one sequence, 4, 2, 1, 3. And as I said, I've switched the way I denote these things. And I go next to the sequence 4, 1, 2, 3. Each of those sequences is a node on a network. The nodes are connected if they occur one after another. The weight of the edge connecting those two nodes is how frequently I see that transition. All right, so the network down here now describes all of the properties that are induced from the deterministic map that you wouldn't see on a random sequence, and describes exactly what's going on in that map, up to some granularity. Right? And that's the key difference between this and things like Tarkin's theorem. I'm deliberately imposing a whole bunch of stuff here in terms of this. I'm reducing all the information in 4 real numbers to a permutation of the numbers 1 through 4. I'll skip over that, but then I'll show you the picture instead, because the pictures are much better. Here on the left is a picture of essentially that map there. This is a logistic map, and what you see are the different permutations of the integers. The size of the blobs and the colour of the blobs is how frequently they occur. The lines linking the blobs are the transitions that are permissible. You can see self loops because that means 2413 will be followed by 2413. And you see transitions amongst these things. So this looks a lot like a Markov transition matrix for those who do those sorts of things. But it's characterizing the transitions that can occur in the dynamics. Obviously, there's a few choices that I've made here in terms of choosing 4. If I choose 10 and choose instead of 4, well, how many permutations of numbers 1 through 10 are there? Quite a few more, right? And this is some of them. The fact that it looks like Tasmania is just a coincidence, but each of those is a different permutation sequence, and I've got transitions between them. So I've got this, when we came past physics, they're doing something with microscopes. I've got this microscope. I can look at the dynamical system. I can look at it at this resolution, 1, 2, 3, 4. Or I can look at it at this resolution, 1 through 10. Why would I want to do that? Well, I only want to do this if I've got enough data to do that. Right? Remember I said the time series is actually finite? I'm estimating a transition. I'm going to do that up to the limitations of the data that I have. Just for the sake of showing you some more pretty pictures, I do the same thing with Lorenz's system. That's when we started with, the butterfly wings. Again, with 2 different resolutions, a fairly coarse resolution, and you can see, well, in both of them, in fact, you see some symmetry. This one looks pretty, that one looks less pretty. What I want you to see here is that there's structure, but we're not exactly at a stage of quantifying or describing that structure yet. So what we can do to quantify it, though, is estimate things like entropy. Right, so a very simple quantity. I've got probabilities of each of those permutations occurring. I can look at transitions between those permutations. I can look at the probability that those transitions occur, and I can compute an entropy based on how those transitions occur. And the value that I will get for this entropy depends on how chaotic the system is, in some sense, which I can make rigorous if you ask me. There's various different ways which you might want to define entropy. There's 3 of them. When I go and compute it, well, I'll just focus for the time being on the picture on the right. So this is a chaotic system. This is actually the Rossler system, which is a different one again, but it's a chaotic system. I'm increasing a bifurcation parameter. Each vertical slice is, in the grey, what can happen in the real system. The black line is something called the Lyapunov exponent. That measures sensitive dependence on initial conditions. It's a standard property of chaos, which is how fast things spread apart. And this is the kind of gold standard in estimating that quantity from that data. This is permutation entropy. Right, so it's giving you the same characteristic, I would say, at least as robustly as the actual estimate of Lyapunov exponent. I want to show a couple more pretty pictures before I finish, and I'm quickly running out of time, so I will move forward, but I do invite questions if you want to ask about these things. You can also estimate Lyapunov exponents directly, because remember, underneath all of this, I've got particular permutations, particular states, and transitions between them. So if my last state, the minus k state, if my last state was this, my next state was this, given that, so what is how often do I see this state following this state, given that I've seen the first state? Right, that's the measure of how much you're spreading out. And you can use that to estimate Lyapunov exponent. and you can do the same sort of calculation again. The only thing to take away from this picture in the 2 minutes I'll show it to you is 4 different systems, 4 different simple maps, because this only really works for simple maps because Lyapunov exponents are quite hard. Different estimates, the true value is the red line, and of course the black dotty one is our method, which is better than all the other methods, but still hard to do. Now where I want to finish though is not with Lyapunov exponents, but in some more recent work. And so when I say recent work, I'm going to start with this theorem from 1890. So I guess Poincaré is probably familiar to most people in this room. This is, and if anyone speaks French, and I know some of you do, and if I've Google translated it, please let me know. But I believe this is Poincaré's recurrence theorem from Poincaré's original treatise, which he was being asked to solve the 3-body problem for the King of Norway or Sweden or somewhere. He didn't quite do that, but he got a prize anyway for doing a bunch of other things. One of the things he did was this recurrence theorem. Another thing was invent chaos theory, but the theorem basically says if I've got one of these chaotic systems and I've got these blobbies moving about, if I take 2 blobs that are close together, they will, well, I can find sets such that the blobs will get close to those sets and diverge from those sets and come back to those sets again and again and again. Things will recur. Right? Imagine those blobs moving about. I can pick a subset of that space and I can say, I know that my blobs are going to come into this space, leave it, and come back again. So we can look at that. And what we're doing right now, I'll skip over that one. Sorry, Zara. That's too hard. This one I like much better. I put it on a black background because it looks prettier and there's too many colours going on here. Here is the Lorentz system. In the different colours here are blobs corresponding to a particular permutation sequence, a particular ordering of the integers. So all of the points in pink, they are 1, 2, 3, 4s, for example. All of the ones in green are 4, 3, 2, 1s, or something else. Right, so notice first of all that there's pink here, and there's pink here, and there's no pink here, there's no pink here. So there's colours that are here, and colours that are here and here. I take one of those sets of points. And now when I say I'm doing the same thing as Lorenz was doing, because it's actually Zara that was doing it, not me. I take points in that one of those sets, and I look at when a point is in that set and when the point is next in that set. Right? And so that's what I'm plotting here. This is the x value when it's in the set, and this is the x value when it's in the set next time. Right? And just like Lorenz's picture at the start, and I can tell you why this looks exactly like Lorenz's picture, which was that one hump map. Just like Lorenz's picture at the start, this describes the dynamics of the system and what's going on in it. So I know that if my value of x starts out as low, then it can stay low, stays low, gets a little bit bigger each time but stays low, gets bigger, stays low, gets bigger, reaches a point where suddenly it flips. Right? When it flips, that actually means it's out here. And when it's out here, it can either flip back, if it's in this region, or it can stay out here. And it can either stay out here and gradually get back, smaller, or it can flip back. Right? So you've got this stretching and flipping, which is what is generating the chaos, described in this nice simple map which we've got from the data. Okay, I think I've just about worn out my welcome, and so I will shift to one slide with applications, and well, that's them. Right? So there's a whole bunch of applications, there's actual real data, and each of these applications to a greater or lesser extent uses methods like this. I won't talk about any of them now, but thank you for listening.
Okay, any questions or comments?
Do you know anything more about Ellen Fetton's story? Was she the one that reran the configuration?
I'm not sure whether it was her fault or whether it was Lorenzo's fault. So I don't know who's to blame for that. All I know is what I got from Wikipedia, which her mother was a concert cellist or something, and she worked briefly at a university somewhere, but before taking up a, let's say, less academic job. And that's all they wrote. Ed.
When you were doing the logistic maps, and there was a lambda, so it has certain structures. Is it sensitive to those sorts of?
To lambda?
Yeah.
So essentially.
So is that the same lambda?
No. So this is a different one, but I'm going to use this picture because it looks the same. When you change lambda, you change the actual chaotic dynamics. At lambda equals 4. You are somewhere over here on the right, and the whole interval gets mapped onto itself, and it's all mixing and it's all chaotic everywhere. When lambda is less than 4, so you imagine the parabola doesn't quite go all the way to the top, so you're only mapping onto a subset of the interval. You don't quite get the full extent of the chaotic dynamics. If you scale lambda back further, you get windows of different periodicity, including period 3, surprise, surprise, and if you scale it back far enough, you get this period doubling bifurcation. So it goes from, for some particular value of lambda, the map is period 2, and then it goes to period 4, period 8, period 16. For some reason, I'm having trouble with doubling numbers, period 32, and so on. And so that's what's going on in here.
So can you let the data sort of inform what that should be?
So this is a generic characteristic of one-hump maps in general. Right? Even the rate at which the distance between going from period 1 to period 2, and from period 2 to period 4, and so on. This is an invariant constant. It's the Feigenbaum constant. Right? It's a fixed ratio. And so if we're observing data, we would probably think that we're interested in a couple of things. We're interested in characterizing the system that generates the data, so that is, what is lambda? And then we're interested in trying to figure out when lambda changes. So you would look at the data, measure your lambda, and you can do that. That's actually pretty easy to do. If you know that it's that shape map. If you don't know that it's that shape map, then you need to use things like measuring entropy and all the other stuff I'll talk about. But you measure some quantity, and then you see when that quantity changes, and that tells you that lambda has moved on. Yeah, Jimbo.
Yes, you did mention, everyone possibly should be surprised about this theorem.
Yep.
Proved by Lee and York, the period of 3 implies chaos. The paper is quite short, one can go through the math, but what's your explanation and why? How does that imply it would have any end period if it has 3?
So it's actually a special case of something called Tchaikovsky's theorem, which is a more complicated thing to prove. It's not a special case. And what that showed is that there's a strict ordering of periods. Right? So if you got period 2, then you've got, and so on and so on. Right? And so there's the strict ordering, and at the very end of that strict ordering is period 3. If you've got period 3, then you've got all of the other ones. Exactly why that is, it relies a little bit. What it's relying on is the fact that you've got this map on the interval, which is mapping some part of the interval onto itself. So it's got to have some level of folding over in that interval, in the interval map, and that's what's actually causing this. So think about the special case of just a one-hump map, like the logistic map going onto itself. So you stretch everything out from 0 to 1 to 0 to 2, and then you fold it back over to 0 to 1. Right? And now, if you look at, and this is probably an easier way to think about it. I'll show you this picture here. So this point here is the period 1 point of the logistic map, because the next iterate is equal to itself. Period 2 points are these three, including that period 1 point, which by definition is not period 2. So you get 2 new period 2 points, and so on, right?
Yeah.
Yeah. So it's the combination of that folding over in your restricted domain, giving you these increasing period points. That's about the best I can do without a pen and paper.
So the number is 3.7 something, right?
Well, so the lambda here in this diagram is just a little bit less than 4, but that's, I think I just did that just because I had trouble with the axes on the graph rather than for any deep, meaningful reason. Yeah, Melinda.
So, I was curious, I'm obviously going to ask an applications question. Right, so the data sets that we're talking about, this works on deterministic non-periodic data.
So
Or
it,
are these methods applicable to all data? And if it is the former, can you give me some examples of deterministic non-periodic data?
okay, so it's the latter in the sense, so it's the former, but it's the latter.
Just not the answer.
Yeah, so the whole reason behind constructing these permutations and looking at these transitions is it's a coarse graining of the dynamics that we start with. In the strictly mathematically correct sense, the Tarkin's theorem and all of that stuff, it's only going to work for purely deterministic signals, right? So you can't have noise. You've also got to have infinitely fine sampling and infinitely long, right? The reason, yeah, we don't usually get them, not even from the fine companies on the screen behind me, even though they may think, yeah. But this is being recorded, so yeah. So we don't normally have those, and that's why we did the coarse graining, because the coarse graining is a way of smoothing out the noise, allowing you to get a robust estimate of a approximation to the dynamics. So the whole point of these methods is that the hope is that they will work for data that's finite, contaminated by noise, and whether or not it's aperiodic is not really an issue. It also works for periodic data as well. It's very simple. For periodic data, it's actually simple. You're going to get so for periodic data, your network is going to be a circle because you're going to go through a set of states, right? For those things, it works for them as simpler. The kicker is the stochastic part, if you've got noise. You always have noise.